So we've covered the intuition. The complex math is stuff you've probably already seen back in high school, but I'm going to review it quickly. We'll talk about notation. So what we've done now, big picture, is we've changed manipulating cosines and sines into manipulating complex numbers. So we're going to need to talk about how to manipulate complex numbers mathematically. So here again is our real part of a complex number. And here's our imaginary part of a complex number. And we can equally well represent it by saying it has a magnitude and this angle. I didn't draw it particularly well. I meant to draw that A down here. Okay, so rectangular notation is A plus JB. Polar notation would be C at an angle of theta. And this is if it's in radians. And we could also draw it as C at an angle of theta if we've got it in degrees. Now, the unspoken word of electrical engineering is that this is our preferred way of drawing things, of notating things. So as I show you different ideas, always keep in mind we want to move back to this representation. It'll become much clearer later why we want to do this. There's one other one, which is called complex exponential. You might remember this from EE223. It's just another way of drawing what polar is, except it's with e raised to the j number, where this theta is always in radians. And what we're saying here, this is actually what it is. It's because Euler, 200 years ago, discovered that e to the j theta is equal to cosine of theta, a real part plus an imaginary part. And so if you could multiply this by a c on the outside if you wanted to. And now you've recreated what we talked about in the previous page, where this is just another way of writing c at an angle of theta, and it has a real part of this, and it has an imaginary part of, I'm going to exchange the j and the c to write the j first, and then the c, and then I can say it has an imaginary part of this, which is just what we talked about last board. You could actually throw this into MATLAB if you want to, as an example. You could say that 5 at an angle of 90 degrees is the same thing as 5 at an angle of, Linda, what's 90 degrees in radians?
Pi over 2.
Pi over 2. And so in MATLAB, you could say, you could evaluate that in one of two ways. One way is to say 5 times the exponent of j times pi over 2. And that's a perfectly valid way of, here's the real part, here's the imaginary part. We've got 5 at an angle of 90 degrees. So here's our point. We are 5 units high. So this is one way you could write this complex number in polar notation. But who have I not called on? Connor, what's a simpler way to write this number in rectangular notation? In rectangular notation, how much real part does this number have?
Would it just be the pi over 2?
Well, how much? So it's 90 degrees up, so it's on that j axis. How much real part does this number have? Here's the real axis.
0.
0. So it's not real at all. It's purely imaginary. How much imaginary does it have?
J.
It's just J. It's in fact, it's going to be J5, right? Because its magnitude is 5. So if you put this into MATLAB, MATLAB will return that you've got J5 back. It'll probably use I instead. But two different ways to talk about the same number. All right. Next thing, I want to talk about converting between forms. We've already talked about that. You can convert to sine cosine form here or to polar notation here. And of course, we talked about this in the context of sinusoids, but the same thing is true for complex numbers. And the simplest thing to remember here is not remembering all these details, but just do the trig. Here's the real part. Here's the imaginary part. Here's the real part is A. Imaginary part is B. And there's your conversion formula. It's right there. So this is the picture you want to remember. And then high school trig will bring you back to step 2. What you'll be doing a lot, though, is mathematics between the two. So let's talk about converting back and forth between different versions using, let me try that again. Let me talk about mathematics, the basic addition, subtraction, multiplication, division, and complex conjugation using these different forms. Let's start off by adding together in rectangular notation two complex numbers. You've been doing this forever. 2 plus J3, 4 minus J6. Who have I not called on? Well, what is this?
You're going to have 6J3.
6, not J3, but
Oh,
we're
minus
adding them.
J3.
Minus J3. Yeah.
My bad.
Yeah. You just add up the real parts and the imaginary parts. So that's easy. Now in polar, I'm just going to say it's hard. It's not obvious how to do it in polar. If you've got something like 2 at an angle of 13 degrees plus 6 at an angle of minus 7 degrees, not easy. But it is easy to do if you're looking at the graphical approach. The graphical approach to adding two numbers, if this is your Z1, think about this as being a vector. And let's say we had this other Z2. I'm going to draw it in a different color so it's clear. We're just going to move this vector, this Z2 vector, so its tail is now on Z1's head, and our resultant vector of the product, the resultant vector of the sum of the two will be, if this is Z2, then the orange will be Z1 plus Z2. So it has a nice graphical interpretation. I'm not going to do subtraction. You can see how subtraction follows from the sum. I will talk about doing multiplication though. Let's go back. Kyle, how would you multiply these two guys? These two complex numbers in rectangular notation.
It's been a while, but I'm going to go ahead and say that you essentially just use something similar to distributive property.
Yeah, exactly. Or FOIL, right? You'd say 2 times 4 is 8. And then you'll do the last. Minus J times plus J. Anyone? What's minus J times plus J?
Just J.
Minus J.
Just,
Minus J.
oh boy. All right,
Minus
let's
J. I'm
let's take a
agreeing with that.
little aside over here and say J is just the square root of -1. So therefore, what's J squared going to be?
-1.
Just
One.
-1. So what would minus J squared be equal to?
+1.
+1. Yeah. So now let's get back to this thing. What is plus J times minus J?
0.
One.
So we just said
One.
that plus J times minus J is 1. So plus J times minus J is 1. And then we've got 1 times 18.
Negative. It would just be -1.
Well, J squared is -1. We said that over to the right here.
No, no. I'm
So
saying if-
therefore, plus J times minus J would be +1.
yeah. I was saying essentially it's just square root of J. It's just essentially square root of -1 times square root of -1 times -1. And those
That's right.
combined would equal -1 because it's J squared, and then times -1 would just be -J. Or negative, or just +1.
+1. That's right. Yeah, which is what we have. All right. Now let's do the imaginary parts. There we've got a 2 times minus J6. So that will give us a minus J12. And then these two would give us J times +12. And so this whole thing happens to be just equal to 26. So multiplying by rectangulars is nothing more than FOIL. Polar, it turns out to be really easy. If you've got 2 at an angle of 13 degrees times 6 at an angle of -7 degrees, you multiply the magnitudes to get 12, and then you add the angles to get 13 minus 7 would be 6 degrees. And graphical, it's going to be hard. We're not going to touch that one. Now, this is helpful, though, because normally when we're doing electrical engineering, we are multiplying and dividing. Ohm's law is all about multiplying and dividing. It's not about adding. And that's one of the reasons why we prefer polar, because it's so much easier. I'll talk about dividing too. In general, this is sort of hard. The way that you would do it, if you had to divide 2 plus J3 over 4 minus J6, just so you can see it, is you'd multiply both by the complex conjugate of the denominator. That was pretty hard to read. Let me try that again. And I will just tell you that when you do the bottom multiplication, you'll get something that's purely real. And when you get the top multiplication, just like you did up here, you'll get something that's both real and imaginary. And then you can break it apart. But it's still hard. Using polar notation, it's really easy. Let's say you want to divide 6 at 20 degrees divided by 2 at 10 degrees. You just divide the magnitudes, and now you're going to subtract the angle. So 20 minus 10 degrees is just equal to 10 degrees. And graphical, it's hard again. And the last thing I want to talk about with the math is going to be how to take complex conjugates. I know we're almost out of time, but we're almost out of material too. The complex conjugate we write with this little star at the end. And in rectangular notation, it's really easy. You just flip the sign on your negative value. In polar notation, it's also really easy. You just flip the sign on your angle. And graphical, it's really easy too. If this is your number you want to take the complex conjugate of, you just flip it around the z-axis so the magnitude stays the same and your angle becomes negative.